Hey guys, Harry here. Numbers, 2, 4, even 9, they're all numbers, whole numbers. Numbers we use every single day. They're all right, but we can do better. One rung up the ladder from whole numbers, we have rationals, ratios of whole numbers. 1/2, 7/12, fractions. We know these guys. They're fun to have a drink with, but if you really want to party, we got to keep climbing the ladder. Constructible numbers. Now these guys can be made using the same simple operations as our rational and whole numbers: addition, subtraction, multiplication, and division. But the addition of the square root function allows us to make new numbers. Root 2, phi, they're all constructible numbers. If an ancient Greek man can make a number, it's a constructible number. Very cool, but we can keep going. According to the fundamental theorem of algebra, any polynomial with rational coefficients will have either real or complex roots. It is in these roots that we will find our next category of numbers, algebraic numbers. These numbers cannot be obtained using the operations I've mentioned previously. Instead, we get numbers that are cube roots, fourth roots, nth roots where n is bigger than 2. Before we move on to the big boys, let's talk about how these sets relate to one another. Every time we move up a set, we can see that each element of the previous set is still contained within. The set of rational numbers contains the natural numbers. The set of constructible numbers contains the rationals and the naturals. You get the idea. Numbers outside of these sets also have names. Anything outside of the rationals is an irrational number. Anything outside of the constructible numbers is an unconstructible number. Outside of the algebraic numbers, we arrive at the transcendental numbers. The next rung up the ladder is called computable numbers. These are numbers in which, given a set of instructions, you can obtain the number. It may take an infinite amount of time, but it's still possible. Outside of the computable numbers lie the uncomputable numbers. These are numbers so difficult to grasp that I'm not even going to attempt to explain them in this video. The idea of transcendental numbers has been around since 1682, when Leibniz proved that the sine function was not an algebraic function. In the 18th century, Euler defined transcendental numbers in the way that we think of them today. But it wasn't until 1844 when Joseph Liouville formally proved the existence of transcendental numbers. However, he did not have a specific number to show. 7 years later, in 1851, Liouville proved the transcendentality of the so-called Liouville numbers, the first of which being used in his proof was Liouville's constant. Way before Liouville proved the existence of transcendental numbers, Johann Heinrich Lambert speculated that both pi and e are transcendental. He did this in 1768. More than 100 years later, in 1873, Charles Hermite finally proved the transcendentality of a naturally occurring number, e. The proofs for transcendental numbers tend to be lengthy and complicated, far too lengthy for me to put in this video. Some of the proofs are actually relatively simple to grasp. For example, in 1882,
Ferdinand von Lindemann
proved that pi was transcendental. He did this by first proving e to the a was transcendental if a is an algebraic number. So, if e to the a was not transcendental, we know a must be a transcendental number. Using Euler's identity, he was able to prove that I pi must be transcendental, since -1 is an algebraic number. We know I is algebraic, therefore pi must be transcendental. The fact that pi is transcendental allows us to prove a great many things. For example, the impossibility of squaring the circle. One of the most fascinating things about transcendental numbers is just how difficult they are to find. There are more transcendental numbers than there are any other type of number, except we know so few of them.
Now that we've spoken about what transcendental numbers are, let's talk about how many we know and how we can find new ones. I have said that we know so few transcendental numbers. This isn't exactly true. We actually know an infinite amount of them. We have general forms, such as e to the a, where a is algebraic, or log a of b, where a and b are positive and neither is a power of the other. Since these generalities depend on countably infinite sets, we only know a countably infinite number of transcendentals. A countably infinite set is a set which has a one-to-one correspondence with the natural numbers. The sets I spoke about earlier, like the irrational or unconstructible numbers, are uncountably infinite sets, as are the transcendental numbers. So we know a countable amount of an uncountable set. Given the nature of infinity, this is pretty much nothing. There is a list of proven transcendental numbers. Here's Wikipedia's one. It's rather short, isn't it? We can see there are a few general forms in there, but most of them are constants. As I've said, it's very difficult to prove transcendentality, but let's look at a way we can narrow down our search. If S is a subset of the field L, S is called algebraically independent over a subfield K if the elements of S are not roots of a non-trivial polynomial with coefficients in K. That was a bit of a mouthful, but basically we're trying to find out whether or not given numbers satisfy polynomial equations. This should sound familiar, because this is how we define algebraic and transcendental numbers. For our purposes, the subfield K is the rationals, and the field L is the complex numbers. A number is transcendental if the singleton set containing the number is algebraically independent over the rationals. Unfortunately, algebraic independence cannot be used to prove multiple transcendental numbers at once. For example, root pi and 2 pi plus 1 are both algebraically independent over Q and are therefore transcendental. We can make a polynomial with two variables x and y for the two elements in our set that will equal 0 when x equals root pi and y equals 2 pi plus 1. One important byproduct of algebraic independence is Schanuel's conjecture. The conjecture states, given any n complex numbers z1 through n that are linearly independent over the rational numbers, the field extension Q with the addition of e to the z1 through e to the zn has transcendence degree at least n over Q. In our case, the transcendence degree is defined as the largest cardinality of an algebraically independent subset of the complex numbers over the rationals. If proven, Schanuel's conjecture would generalize most known results in our transcendental number theory, and it will allow us to discover new transcendental numbers with relative ease. Transcendental number theory is one of the most fascinating topics in mathematics. It deals with concepts on the very edge of our current mathematical scope, and its complexity makes breakthroughs few and far between. It's fascinating to think that most numbers are transcendental, yet we know so little that we can condense our knowledge onto a list less than half a page long. I've been fascinated with transcendental numbers since the very first day I discovered them, and they fascinate me to this day. I hope this video has fascinated you.